Magnetism field inside a solenoid. We see that the diagrammatic representation of magnetic field of a solenoid has been shown here. Point Q is a point situated outside the solenoid, and outside the solenoid field is in the form of curved closed loops, while point P, which is situated inside the solenoid. Here the magnetic field is uniform and the form of parallel straight lines. So this is how we understand diagrammatically. As you can see, there are several turns of the wire shown here. All these are turns of the wire. Okay, and the magnetic field due to each turn adds up to give the total magnetic field. Okay, so here the magnetic field of first turn in this way, of all the turns they add up and we get this resultant magnetic field in the form of closed loops. So let us derive the expression for magnetic field inside the solenoid. Here you see the diagram. We have taken inside of the solenoid where the magnetic field B is in the form of parallel straight lines, which represents a uniform magnetic field. As these parallel straight lines are there, they represent uniform magnetic field inside the solenoid. Now here the direction of current has been shown. The dots represent the current coming out, here the dots on the one side, and crosses represent the current entering into this surface or entering into inside this surface. Okay, so this is the direction of current flowing in the different loops or all the loops of the solenoid here. Now we consider or we take an Amperian loop which has been labeled as A, B, C, D. So this rectangular Amperian loop, the length of the side CD and AB has been given as or assigned as H. Now our point Q again, which is situated outside the solenoid, and point P is situated inside the solenoid. We are interested in determining the field inside the solenoid. So let us do it. Here we see that in the given Amperian loop ABCD, the field along side CD is 0 because side CD is situated outside the solenoid, and we have already taken a simplification or approximation that field outside a solenoid is 0. Field outside solenoid vanishes. So the contribution on part of the side CD for field is 0. Next, the sides AD and BC. As you see that the magnetic field here is along the horizontal direction only, in the form of parallel lines along the horizontal direction. So its perpendicular component is 0. The direction of magnetic field, suppose this is x direction or horizontal direction. So magnetic field is directed only along horizontal. So its perpendicular component is not present. That's why the transverse component or perpendicular component of magnetic field here is 0, and hence the contribution towards side AD and BC, or the magnetic field corresponding to sides AD and BC, is 0. So the only contributing side towards the magnetic field is AB. That means only field along AB is contributing here. So the effective length of the Amperian loop will only be the length of side AB, this one, and the length of side AB is equal to H. So here we have to take the effective length of this Amperian loop equal to H. This is what. Alright. So now we consider the effective length to be H, and we can easily find the total enclosed current. How do we find the enclosed current? Here enclosed current I is N into H into I. Now how is this? Here N is the number of turns per unit length, and the total length is H, which is the effective length, as I have mentioned here just now. So the number of turns per unit length multiplied by total length. It gives us the total number of turns, n into h. So here total number of turns n into h multiplied by the current in the solenoid I. Okay, so total current in the solenoid is I, but we are interested only in the current enclosed by our Amperian loop ABCD. That's why we have taken only the number of turns which are associated with this Amperian loop ABCD. We have not taken the total current all through the solenoid. We have taken only the current which is contributing for this Amperian loop, or which is associated or corresponding to this Amperian loop, and hence we have taken the net enclosed current as total number of turns NH multiplied by the current in the solenoid, that is I. Alright, so this is what. Now, when we use Ampere's circuital law, what does it say? Integral B dot dl is equal to mu naught I. This is what? Closed loop integral B dot dl is equal to mu naught I. So we are already done with this part, B dot dl and everything, because here the angle theta between B and dl vectors is 0. So already all this is done, and for taking integration here, we are taking the total length on taking integration or corresponding to integration. So total length or total effective length of capital L equal to H has already been considered. So when we apply all these factors to Ampere's circular law, B dot dl is equal to mu naught I, we get B into L is equal to mu naught IE, where IE is the enclosed current, L is the total length. And when I put the values of L and IE from our previous discussions, then what do I get? I put the value of L as H, and I put the value of IE as mu naught NH into I, as we have already discussed. Now, as you see, H gets cancelled on both the sides, and what we have here is B is equal to mu naught Ni, which is the magnetic field inside the solenoid. An important expression for magnetic field inside the solenoid. Here, B is the magnetic field, mu naught is a constant, N is the number of turns per unit length of the solenoid, and I is the current through the solenoid or current flowing the solenoids. This is the expression for field inside the solenoid. Thank you. Like, share and subscribe to the practical side for more interesting and informative videos.